What if I told you the universe isn't silent? For most of history, we thought it was. Space looked like a giant glowing painting. Beautiful, but still. Then in 2015, everything changed. We didn't just see the universe, we heard it. That sound? It was the final scream of two black holes crashing into each other over 1 billion light years away, and somehow Earth heard it. Welcome to Gravitational Wave Astronomy, where we listen to the heartbeat of the cosmos. So what are gravitational waves? In simple terms, they're ripples in the fabric of space-time itself. Imagine throwing a stone into a calm pond. The ripples spread outward. Now replace the pond with the universe, and the stone with a cosmic collision. Einstein predicted them in 1916, over a century ago. He said when massive objects like black holes or neutron stars move or collide, they disturb space-time. But the ripples are incredibly faint. So faint, Einstein thought we'd never detect them. He was wrong. Enter LIGO, the Laser Interferometer Gravitational Wave Observatory. 2 facilities, one in Washington, one in Louisiana, each with vacuum tubes 4 kilometers long. Lasers bounce between mirrors, measuring changes smaller than the width of a proton. That's like measuring the distance between Earth and Alpha Centauri, within the width of a human hair. For years, LIGO waited in silence. Then, on September 14th, 2015, boom, the first confirmed gravitational wave passed through Earth. It came from 2 black holes, each about 30 times the mass of our sun, colliding at half the speed of light. That single ripple traveled across the universe for 1.3 billion years, before gently squeezing and stretching Earth itself, just a tiny amount, but enough for LIGO to hear it. The signal lasted less than half a second, but it rewrote physics. We had finally opened a new sense. Before, astronomy was all about light, visible, infrared, radio, X-ray. Now, we had a whole new messenger, gravity, and what it told us was incredible. The first detection, called GW150914, wasn't just proof of gravitational waves. It was proof that binary black holes exist. It was proof that we could detect them, and it was the beginning of a new era. Soon, other observatories joined in, Virgo in Italy, and later Kagra in Japan. With 3 or more detectors, we could triangulate signals, figure out where in the sky they came from, and then came the big one. August 17, 2017, 2 neutron stars collided. LIGO and Virgo picked it up. This time, the gravitational wave signal lasted longer, about 100 seconds. And then, just 1.7 seconds later, NASA's Fermi telescope detected a burst of gamma rays from the same spot. It was the first time we saw and heard the same cosmic event. Telescopes around the world scrambled to look, and what they found changed science forever. They saw a kilonova, an explosion so powerful it forged heavy elements like gold and platinum. That's right, the gold in your ring? It came from a neutron star explosion. In that moment, we confirmed that neutron star mergers are the birthplace of the universe's gold, uranium, and other heavy elements, all created in cosmic death. But the science goes even deeper. Gravitational waves don't just tell us what happened, they tell us how the universe works. From these signals, we can measure the masses and spins of black holes, the inner structure of neutron stars, how fast the universe is expanding, whether Einstein's theory still holds under extreme conditions. Some scientists even hope to detect exotic objects like boson stars, primordial black holes, or evidence of extra dimensions. And we're just getting started. Future missions are already on the way. In the 2030s, the European Space Agency will launch LISA, a space-based gravitational wave observatory. Instead of kilometers, its arms will stretch millions of kilometers long. It will float in space, following Earth's orbit, listening for ultra-low frequency waves, the kind made by supermassive black hole mergers. On the ground, the Einstein telescope and Cosmic Explorer will take sensitivity to the next level, allowing us to detect every black hole merger in the observable universe. Together, they'll give us a full gravitational map of the sky, not just where things are, but what they're doing. But what about the really big questions? Can we hear the echoes of the Big Bang? Could there be a cosmic gravitational wave background, like the hum of the early universe still rippling around us? Some theories predict it. Others think gravitational waves could reveal dark matter interactions, or hidden forces we've never seen. Even time itself might be more flexible than we think, warped and stretched by ancient gravitational storms. Gravitational waves may help answer some of the deepest mysteries in physics, or they may just give us better questions. So why does it matter? Because this isn't just science, it's storytelling. When we detect a gravitational wave, we're hearing the ending of a cosmic drama. Stars that lived for billions of years, dying in a final burst that bends space itself. And sometimes, From their destruction comes creation. Gold, light, energy, knowledge. We're no longer just looking at the universe. We're feeling it. We're tuning into a cosmic symphony, a soundtrack that's been playing since the beginning of time. And the best part? We're only at track 1.